So hi everybody, and today I will be presenting FedMask, the Joint Computation and Communication Efficient Personalized Federated Learning via Heterogeneous Masking. Sorry. So this is the outline of the presentation. We will be talking about the motivation first. So we will introduce the concept of federated learning. So what the basic concept is there's a central server who sends out tasks for those local devices to train, and each device have their own local data. And after they are done with their training, they will update their results back to the central server, and the central server will collect all these information, and then they can provide a new model, and they can be then sent back to the data to do the second round of training. So this is pretty much the concept of federated learning. And there is some challenges for federated learning. And the first one is the personalization for heterogeneous data. So if at each device they have their own data informations, and if some of them are too biased, or they have they're very different from each other, and it can affect in the accuracy of the training. Also, the computation is one of the main concerns for every device, and including this big federated learning training. And also the communication, which is when it happens when the devices, the local devices and the server, when they're doing the transmission, the communication costs must be considered a big consideration. So here's are some figures, for example, like how these are affected, and also why there are challenges for federated learning. So what we want to do is have, for this paper, FedMask, we want to have that each device can learn a personalized and structured sparse DNN, and which affects and reduces the computation and communication costs. So that is the goal of this paper. And here's a form of telling this is the work of this paper, which is FedMask, and we consider the computation efficiency, the communication efficiency, and the personalization among all those. And the other four, these are in comparison of former works, and we will be talking about them in the implementation section. Okay, so now we'll be talking about the FedMask design. So the overall framework, this is a bit overloaded, but we'll be talking about the details of each. So basically, first you have this central server which initializes the model, and then for each device we perform a one-shot pruning. This is a one-time thing. You only do this once. The purpose of this is to initialize some of the factors we'll be talking about later. And then after the pruning, we will be doing the local mask optimization. And after optimization, we will do the we will do the aggregation of it. So the second step, optimization, and the third step, aggregation, which is 2 and 3 in this figure. Those two are going to repeat themselves until we reach a final conclusion. So after we do all the optimization aggregation several times, we can then finally generate a personalized and also structure sparse model for each device. So as you can see that each device, they have a different personalized model. So this is basically the full concept of the FedMask design. And now we will be talking about, so before we just explain all this, we'll be talking about what is the key concept of this, which is mask binary optimization. So given this is a simple example. So given we have a real fixed value weights, so this is a model with the weights individually on here. And then we have this optimal binary mask, and which these are considered to be binary. So what that means is that this mask is there's only two outcomes, which one is 0 and 1. So the yellow ones here are 1, and the gray ones are zeros. So after the element multiplication, you can see the result of this mask weight will be those with the green ones. So all those, all these three are reduced to 0. So this is what is so important about this is that we will use this to transmit and aggregate in the whole framework, and to determine what this mask is. So the ij, it means the ith column, j row of the mask. It will be 1 if the original the real valued mask is over a threshold, and if it's 0, it is 0 if the mask is lower than the threshold. So this mask, this real value mask, this is predetermined basically. So we will be given a initialized real value mask, and then we will go into this threshold. So this threshold in this paper, it is designed to be 0.5. So if it is the corresponding unit is more than 0.5, it will be 1, and if it's less than, it will be 0. So that's how we get this binary mask of this. So the first thing we have to do is we actually need to initialize mask for each devices to do, and in particularly a heterogeneous mask for each device. So every device, they have their own heterogeneous binary mask. So what do we do with it? It's the first step of this, which is the one.
Huai-an, can I ask, can you go back to the previous slide here?
Yes.
So here, the mask is defined over the edge or defined over the load, over the neuron. So, so if here, for example, okay, specifically, you say here you have a lot of edges here, right? So according to your mask, you will delete some edges. That's fine. But if you see the figure here, looks like they are trying to say, okay, I'm going to hide this one, hide this one, hide this one. And then all the edges that are associated with those neurons got pruned from the figure. This is what the figure shows. Okay, so my question is that, are they defined the mask based on, so okay, so on this hidden layer, whether this neuron gets masked or not, or they are trying to say, okay, I'm just focused on the edges between those two layers. You get my point?
Okay, I think they focus on the neurons. So they pretty much because the neurons, these are masked, they are zeros now, so they will no longer have any real like impact to the other neurons. So that's why the lines are different here. So I think they focus on the neurons first, and those edges, they are just because these neurons are now 0.
Okay. So so do they use the word called dropout? So I mean, in the paper, do they mention about the dropout?
No, actually, they only say that these are. They actually mention like how these two, the mass is there only 0 and 1. They didn't mention.
Okay. I see.
Yeah, I think Dr. Gore, later you're going to be fine. It's a little bit different from our understanding. First of all, they try to mask the stuff. I mean, all the devices, they use the same model. You see the full connected model, they use the same model. So it's really hard to say they define the mask based on what. Different device, they define the mask differently. But it's really hard to say. I think even in this paper, they didn't explain that based on what they define the mask. Our guessing is based on the device kind of capability, for example, computing capability or whatever. They define, or say one-shot pruning things, they define the mask. That's the thing. The second thing is they didn't exchange the local model updates. In other words, they didn't change the called pruning, dropout, the gradients. They exchanged the mask. So, but anyway, you just wait for Huai-an to proceed, and you're going to say it's different from the general file learning framework.
Yeah. I will be talking about
Yeah.
that later.
No, even I get a point here. Yeah, it looks like they are very maybe it's very different from what I saw before. But even according to Huai-an's explanation, if they trying to decide the mask based on the neurons, but then if you see the formulation here, they say, well, this one larger than someone here.
No. They don't define the mask based on the neurons, according to my understanding. What this equation shows us, like, if the neuron value is something larger, is the mask value or neuron value?
Yeah, that's what I'm.
Yeah, this is about.
This is a neuron value or mask value?
This is the neuron value. Like IJ means the corresponding I row and J column. So this is the neuron of it.
It's a neuron value.
Yeah.
So this is the.
Yeah. Go ahead.
This is the activation value. This is the activation value of neuron. I think it's not the column. Actually, Huai-an, I want to say it's column and row. It's basically like which layer and which neuron of the layer. You can point this. It's not like a row and a column. Actually, it's most which layer, and on this layer, the J's neuron. Maybe this is more like the activation value up. It's basically like the output from this neuron, and then you also have a weight here. You have a lot of weight here. So basically, maybe according to Huai-an's explanation, maybe it's basically check the activation output from this particular neuron.
Yeah.
And then they will compare it to, because this one, the output is always between 0 and 1.
Yes.
Because you always go through a softmax or whatever, or sigmoid or ReLU. I mean, not softmax, ReLU. Then it's between 0 and 1. So they set a threshold, maybe 0.5 or 0.2. So then they will make this decision. So in this case, it makes sense. Yeah, it's basically like because you are based on this activation value. So if this activation value is less than 0, less than tau, then the output is always 0. Then the 0 times whatever weight is also give you a 0. So that's why it's equivalent to delete all the edges between those two neurons.
Yes.
Yeah, I think that makes sense if that's the case.
Okay. Yeah.
But they have the same initialization, or they have the different initialization for the mobile device. I mean, for the devices. Okay, you can go ahead to the next slide. We can check.
Okay. So this is the binary optimization, and so now we're talking about the one-shot pruning here. So what it does is initializes a heterogeneous mask for each device. And then it is based on the global mass in each device. So how they generated this heterogeneous mask, they only mention about the concept. So it's basically based on the each characteristic of each devices and the mass they just determine about. So what one-shot pruning does here is they create a heterogeneous mask for the device later on to perform the optimization, which is shown in here. So
I'm a little bit confused about the one-shot pruning stage. So, after the one-shot pruning, right? So each device cut off some neurons, right?
yes,
But they cut off the neuron differently, right?
yes,
And according to the cutted new local model, they generate the initialized mask according to previous slides, right? Is that true?
yes, yes,
Oh, okay. And later they updated the mask.
yes.
You know, according to exchange stuff. Okay, okay.
Yeah.
Okay,
So they
gotcha.
basically, they basically generate those two for the optimization. For one is the prune model, and the other one is the initialized mask. Yes, that is the job for this one-shot pruning. It's a one-time thing, basically.
But they do the one-shot pruning differently, right? But all the one-shot pruning, they are from the same initialized fully neural model from the centralized server. Is that true?
Yeah, all these one-shot pruning, they are from the same initialized model and also the same mask. So all of them are all global and they are all the same. And but because different devices, they generate different models. Yeah.
Paula, I want you to keep one question in your mind, right? So you're most familiar with the personalized pair learning in our group. So think about this. Is that the similar things to the pair learning, you know, the paper you have read? If yes, why? If different, could you also please provide certain kind of explanation afterwards?
Okay, sure.
Okay, yeah. Okay.
Yeah.
Please go ahead.
Okay, so I'll continue. So this is the first step, one-shot pruning. And the second step is right here, which is what we just mentioned there. So this step is the local mask optimization and the transmitting. So what it does, as you can see, that it optimizes and it transmits the binary mask. So in this place, you can see 2B, they only transmit the binary mask, which is 0 or 1s. So in comparison to other federated learnings, they transmit local updates like parameters, and in here they only have this binary mask. So overall, this is much more light, and that is why it claims that it improves in the communication.
So do you mean like here the binary mask is similar to the gradients? It carries similar information that the gradients carry, just like in a lighter way?
I would say that these binary math, they pretty much don't, they are much of a concept of like a structure of the model, because they're all in 0 and 1s, and they don't really carry that much information for something like gradients.
Then in this, is this supposed to replace the original gradient updates in federated learning, or this is like a separate stage? So is there a federated learning process here? Because like from the figure, what I can see is the only part that are federated are these binary masks. I don't see like what in the previous, all the previous approaches of federated learning that what we are familiar with are like they exchange those gradients or model updates in order to learn information from others, right? But here they are only exchanging the binary mask. Do they still have a part that exchange models, or like here they are trying to use this binary mask to replace those one?
They pretty much just replaced it with the binary mask. So as you can see, all those transmission and also the third step, the aggregation, all the information are based on those masks they provide. So they pretty much provide only the structure of those models. So as you can see, the initialized models, they weren't even changed at all. Like
so is it here like so is it similar, like you are now actually not having, so do they still have model weights, or their model or they only have the parameter for their model are just zeros and ones?
Yeah, they only have the parameters and they only have the parameters in the model. And all the weights are already determined in the initialized model.
And Dr. Gong, I don't think that he has a perfect answer for your question. Actually, that's the question exactly we want to discuss with all of you guys. Yes, you're right. Here, they only exchange the structure. I'll say they only exchange the mask. They don't exchange the gradients. For your question, if that equals to gradient exchange, we don't know. They didn't provide any kind of a theoretical proof for that. But from empirical results, because it's SenSys paper, right? From empirical results, it seems it's pretty good, but we don't know reason why.
Yeah, the results are pretty decent.
Yeah. Then what are their initialized model? Is that a random model or it's like pre-trained model here? Like
that's
in
very,
the
that's very good. That's very good question.
Yeah, the paper doesn't mention it either. Yeah.
No, I think Dr. Gong's question is after the one-shot pruning is like the other day when we discussed with Dr. Fu, you and me. For that model, it's a kind of very well-trained model, pretty good model. It's a very, rough model after one-shot pruning.
Okay, so they didn't really provide this kind of information, but in order to have the results to be that good, it is really possible that they just use the pre-trained model as this one, because they didn't really mention like how this model is pre-trained or any. They only mention that all those models are initialized, and all those initialized are done with are composed and with each devices.
That's your understanding, you're guessing, right? It's not what they provide.
Yeah, they didn't provide, so it's basically on my guessing.
So your guessing is one-shot pruning and the initialization is pretty good.
Yes, that is.
Yeah. Sorry, go ahead, Dr. Gong. Yeah.
Yeah, so I guess here there are two possibilities, and I think the most possible is that they are just they're just trying to learn a personalized mask in a federated way or so, but I don't know if that makes sense. And the second possibility is like, because I remember before I heard like Microsoft or some place, they use some binary neural network to train it so that like each node the weight are only either 0 or 1. I'm not sure if that's related to this one as well.
Okay, I think what you mentioned about the second one, I think that's not the case here. I think it's more towards the first possibility, which is what Dr. Kuhn just claimed. It's just they
already have a good model.
Yeah, they have a good model, and they train the binary mask in a federated learning way. Because the one you mentioned about which is the binary neural networks, they actually mentioned some of them in the paper.
Okay.
Yeah, so I think this is like different concepts. Yeah.
Okay, got it.
Huai-an, if you think about the let's say, okay, so you are currently let's say for one-shot pruning here. So you say the device 1, 2, 3, they will prune different neurons, right? I think the black one are prune the unit neuron, right?
Yes.
And then each device, they will optimize their local mask in in this step. So what do you mean by, so how do they, I think that whether the mask contains whether this mask contains the information about the data or not depends on how do they optimize this mask. Let's say if they, for example, if the mask are optimized based on the data, then maybe the mask already contains some data information. So by exchange this mask, they will be able to, more like exchange some data information. I think that's why made it work or not. It's based on how do they define this local mask optimization. This optimization problem, I think, is very important.
It's just like if they are choosing the top K, then maybe that reflects some of their local neuronal models.
Yeah. It's more like I think in some paper they mentioned about they just transmit. Remember, they don't transmit the gradient information. They actually just transmit the positive or negative of that gradient coordinate. Remember, it's most like a -1 positive. It's most what is -1 or +1. So they just transmit this kind of information. I think what's the name? I forgot about the name of that approach. It's called I think it's more like the quantization, binary quantization. Binary quantization, right? If you are going to quantize the gradient.
Yeah, that's similar to what I mentioned before. Like so the resulting neural network is going to have like the 0, either 1 or -1, right? But
not necessarily. Not necessarily. That one, the binary quantization is trying to quantize the gradient. The transmitted gradient.
I see.
They are not trying to quantize the weight.
The model itself.
The model. But there are different things. Sometimes there are some papers, I think, they trying to just restrict the weight parameter to be, for example, a discrete, just a binary neural network. I think this is one, not the binary neural network. It's just like the gradient is binary. The binary.
Actually, I thought of what you mentioned just now. But the thing is, if you think about the gradient quantization, right, in particular into very low level to the binary one, it definitely is going to affect learning performance eventually.
Yeah.
But the thing is, let me finish. The weird thing here, this paper, it looks like binary quantization, but the performance is pretty good.
That's normal because if you assume, for example, if they think the model is very complicated, but the data set is very simple, then this is possible because there are a lot of actually redundancy in the model, so that you don't need to worry about the exact value of the gradient or model weight. That's possible. It really depends on the experiment setting.
Exactly. Like that's what I want to say. It's really depend on some hidden information. Like you said, if the data set is simple, right? But the model is very complex. But they do, if I remember correctly, they do the experiments on many data sets, at least the VGG, some big data set, or some other LSTM, some small data set. So I don't know, but that's my doubt as well. My general doubt is similar to gradient quantization to binary one, but the performance is almost to beat everyone.
Yeah, I think I feel that maybe because they know the binary quantization approach, and then they're trying to but binary quantization is just used for the communication efficiency, right? So what they are trying to do, I guess, is that to extend that basic idea to account for both computation and the personalization.
So I think another thing is reason why probably they help improve the accuracy a little bit is it's not like the binary quantization. When you return, you get a global binary quantization, the global model, right? But here they got a mask here. They use the mask times their previous local model for the next round updates. They still keep the real value of the neurons. They don't reduce the neuron value, local training neuron value, to binary values. They still keep the the real value. The accuracy precision is pretty high.
Yeah.
You get what I mean? Probably that one helps. Yeah, that one helps to improve the precision a little bit. Okay. So now we learn a little bit better about the trick.
I think so. You're right. Yeah, basically, I think it's basically like a heuristic, because you are using heuristic unless do a lot of tuning and trying to repeat their results. Otherwise, you cannot you cannot get a lot of things from them because there's no theoretical reasoning there. It's basically like, well, I try this approach, well, it works. And unless they release everything, and then you can repeat otherwise. And also, as I mentioned, it really depends on the complexity of a model relative to the data set, the task.
You're right. It seems that they upgrade the binary quantization somehow, little bit. So yeah, based on the same as, okay. Yeah, Huai-an, did you get our point here?
Yes. Yeah, as you mentioned, pretty much they translate the binary mask only, and they still get the real value afterwards because they use it with the initialized model here. So,
but did you get the binary quantization part? I think that's the benefit of our discussion.
yeah.
According to our last discussion, we I think I thought of that, but I didn't talk that with you.
Okay.
I think Dr. Gu will provide much more valuable information here.
Yes.
Okay. Yeah.
All right.
Please move on.
Okay.
Yeah.
1 second. Before we move on, I have like a couple of things because there were several questions that were raised before. I think first of all, the initialized model here is not trained. It is not a pre-trained model. You can imagine it like federated learning where we first initialize a model, send it to all the users, and then start the local training. So this is the same phase. So we first initialize the model and it is not trained. And after at the one-shot pruning part, it is kind of performed on this initialized model based on their own parameters. And this is not the neuron level of pruning. Like what I see from the paper is this is more on the weight pruning. So the weight pruning will be more like the input to the next layer. So it is more on the connection level. So if the certain weights in your matrix are set to 0, then they will become very sparse and eventually that connection will not exist. So that's why the neurons are marked black, because there is no connections to it. So they're as good as not functioning in that particular round of training. So that is what that signifies. And the other thing is they are sending the masks.
Please hold on. So for the one-time pruning part, I still got confused. So different device prune that, randomly, arbitrarily, or they have some certain kind of strategy to do the. I know the general one-shot pruning. Definitely, according to some empirical records, history, you can do, one-shot pruning for inference or for training stuff. I understand that, but for here, the one-shot pruning follow that one, or they follow, the capability of the device. That's the things I want to know.
Okay, so at the one-shot pruning level in this paper, they have kind of used a mix of a few methods. So what they're doing is each of the device uses their own kind of mask. So it's the m⁻⁴. I think that's what he showed in the previous slides. So you kind of use the real valued mask for each device and you will sort it and do the pruning. So each of them are doing the pruning independently. So it will be completely dependent on what are the kind of, yeah, go ahead.
Yeah, I'm asking about the criteria here. I understand what you're saying perfectly, but I just want to try to know what's the criteria, according to what criteria they do the one-shot pruning.
I think that.
Did they mention that?
Yeah, I thought he probably covered that in the previous slide. So first they defined like the pruning rate for each device, like how we did it in our papers, but we use like a common pruning rate. But in this paper, they're using a pruning rate per device. And that is dependent on like how dense your top layers of your structure is.
Okay, they use the top.
So depending on the density.
Okay.
Yeah, like how many layers you have, you look at that, and then you will try to define a mask, define the pruning rate according to that.
Okay. In other words, they just kind of randomly pick. Okay, got your point. Okay, please go ahead.
Yeah, and their emphasis is that, at the one-shot pruning level, they're not really worrying too much about what is the kind of mask I have to choose, etc. Because they're doing that part in the step 2, I guess, the local mask optimization. And basically, we usually have, hey, Huai-an, do you have the figure 9 from the paper in your slide?
Figure 9?
Yeah, the figure 9 from the paper, do you have that in your presentation slide?
Yes, I do. Right here. This one.
Yeah. So Professor, so this is what it would be like in general pruning and the mass computation. We first take, you can just look at the first column. We take the model, we do the Hadamard product with the mask, and then we get the model. And this model update is usually sent for our federated learning training. But what these people are doing is they're cutting off the last part. They're just taking the part 2, and they're only sending the mask per round, and then they're doing the aggregation of the mask itself. And in the end, they're gonna apply it to the model and they get the model parameters. So that's how the weights are pruned, and they have a very personalized mask, and that's how you get a personalized model.
Yeah, we got this part. Okay. Yeah.
So it will not be binary. The weights will not be binarized. Only the mask will stay binary, but mask is usually binary. It is not different from any other mask that we usually use.
I think what Dr. Guo and I discussed is, like you said, you point out the difference from this one, from the binary quantization, but we just think about, okay, if we just do binary quantization compared with this one, why this one is much better? That's the things we discussed just now. But exactly right. Like you said, because they exchange the mask, but afterwards they just multiply the mask with the model. They still keep the weight value, pretty real. It's not like binary value, so their accuracy or precision probably is higher. Yeah, we got that part.
Yeah. Right. So the only one point that why the accuracy will be better in their case compared to the binary quantization is because the mask is optimized in a very rigorous way. I think he might cover that in the other slides, but yeah, the way you're optimizing the mask, that is making all the difference in why your accuracy is better in this paper.
Yeah, probably you can touch that part, but I don't think it's much different from binary quantization. But binary quantization aggregation though. But anyway, Huai-an, could you go back and continue the presentation? Yeah.
Okay. So yes, after the optimization and transmitting, we will do the heterogeneous mask aggregation. So as you can see in the figure in the left here, this is an example. So all these individual neurons, they won't be updated unless they are overlapped with the neurons. So as you can see in this one, they are those two devices, they overlap. So they will update the average result of this model. And as for the one in the right, they are overlapped with 3 devices, and then they will get the average, which is 1, and update into the binary mask. So to show a better demonstration of how it works, so we have device I and device J, and device I, they have channel 1, channel 3 with those unpruned masks, so the yellow ones. And with device J, you have only this one, this mask here. So what it does is that the server will check whether the masses are overlapped with each other. So in channel 1, indeed the device I and device J, they both have overlap with each other. So then they will update it to the green mask here. So as you can see, this is pretty much a AND relationship. So if the yellow one and the blue one, they are all ones, and it result in ones and a new mask. So as in channel 1, because devices have overlap mask, that's why they updated. But for those without overlapping, so in channel 3, as you can see, device I has a mask, but the device J doesn't have a mask. And in this case, they don't overlap. So that's why after that, they will be untouched. The update they won't have the update. So before the aggregation, device I, it looks like this, and after it, it becomes a new updated version, and also the case for device J. But since they don't update the ones that doesn't overlap, you will have different results in terms of masks. So device I, device J, they have different masks after the aggregation, and all those two, they will be sent back to perform the local mask optimization once again. So that's how they make sure that each device, they have their own personalized structure, but also they can train it and update it. So this is the aggregation part. So
Huai-an, can
yes.
you here? I'm just curious about, for example, here, let's say for this one, if you mask, so when you represent the mask at this load, you are still using, for example, here, this case is more like how to represent this one.
It's a proof one.
Oh no. What I want to say is that, well, I assume that because those structure, they are the same, so you can use a single long pi array to represent their information. That's no problem for that one. However, here the mask, they are in different structure. I mean, for example, this one you only have 4 neurons. This one you have 5 neurons. You have 4 neurons, right? So you have different structure.
Yes.
But for example, for the figure you show here, I assume that this is a mask, right?
Yes, all those are masks. Yes.
So you say the mask, according to your explanation, if they, for example, for channel 1, I have the mask. You have the channel 1, you also have the mask. So we will combine with each other to get a common mask, right?
Yes.
But
yes.
but if you go back to this figure, looks like they don't have the mask structure looks like are different. They are not like always 3 by 3 or 3 by 3 in this form. So how do they represent? For example, let's say, I know that, for example, here you have the blue one, you have the green, yellow one, you also have a black one. So I assume that the value here, they should have 3 different types of values, not just the 2 types of value, not just 0 and 1. Maybe they have 0, 1, and something to represent the black or whatever. You get my point?
Okay. Yes. So based on those 2 comparisons, I would say that they would treat the black ones as 0, but they only need to transmit those they are unproved, right? So they will transmit. So as for example, like if these 4, they represent those 4 in this mask, so the server will get the position and the value for these, and they will compare with others, and those they didn't get transmitted, they will just replace it with zeros. I think what they do here is that if you only transmit those 4 instead of the entire model, the overall communication cost will be reduced with that. But just after the aggregation, they just say, okay, I get these information, then I will treat the others unsent to be zeros. I think that's how they minimize, how they reduce the cost of it. That's what my understanding is.
Yeah, but so let's say what's the difference between this blue one and the yellow one? And then in this case, what does that mean in the figure?
It means for 0 and 1, basically.
But according to your explanation, this one is also 0 and 1, right? This is black is 0.
Yes.
So then this is weird, you know. And that's why I'm saying, because you have 3 colors, and when you transmit them, you need to use for each element, you may want to use 3 different. You know,
no. I think Dr. Guo, for your question, the gray one, still 1. But the thing is, you can say gray one, only 2 nodes, 2 clients, they have the gray one, right? So they aggregate the gray. I think that they want to show that. For the yellow one, 3 guys have that. They aggregate that one. Oh, this is probably,
okay.
yeah.
Okay.
Yeah.
Okay. So
this one represents a kind of a neural instead of a specific 1 or 0 value. You can say the yellow one probably represents the 3 to 3 matrix here, something like that. I don't know, but you know, it's not, yeah.
So you mean all of them? So for example, in this case, all of those one, actually the color one, not the long black one, they are like 1 represented in this matrix.
Something like you have the value. It's not like exactly 1, but you have value. This black one is like, you know, the channel 2, all zeros.
Yeah. Yeah.
Also, you know, in this paper, they assume the server knows the full structure of the deep neural network. Also, they start with the same deep neural network. You know, when they do the aggregation, the server also know, you know, the predefined structure of the deep neural network. They use the same model, basically. So that, you know, even you partially transmit the structure, you know, the server know, okay, which part I need to fill in, something like that. Yeah.
Yeah, I just maybe just the figure issue. Just don't know what's the difference between the gray one and yellow one. But as Dr. Pan mentioned,
yeah, the gray one is like, you know, the 2 people have that. Yellow one means that 3 people have that. That's my understanding. Oh, by the way, the last
it's not that, but still
not that way. Still not that way. Still not that way.
What did they say in the paper? They must have said something in the figure.
I'll say probably, you know, the yellow one represent just like a channel 1 value, 111. No, not that way too.
Wait, but
I don't know.
But actually, based on the paper itself, this is the concept. This is a mask. So which should be equivalent to like the one in channel 1.
Oh, I think we over explain that. I think either gray one or yellow one, it just means it has values. It's not all zeros.
So by the definition of this mask is that the yellow ones are 1 and the gray ones are 0. That is the definition of the binary mask. So that's why in aggregation form, they only have 0 and 1s. So that's why when so that's why when we talk about the, like when they update those, they just update the one in the ones that they actually have. And those prune ones is because of the device themselves. Like the device themselves, they already prune out these.
Oh,
so
okay. I got your part. Yeah.
Okay. So they only consider these for, So I think in terms, answering Dr. Guo's question, I think in terms of result, I don't think the black one and the gray one will make much difference. It's just in the transmission, they only need to transmit these parts. Like, yeah, because like for each device, they already have the initialized, right? They already have the initialized binary mask. So these three, they are guaranteed to be pruned.
Zero.
So
Okay.
yeah, zero. So every time they do this mass optimization and aggregation, they don't need to care about those because they will always be zero. So the only changings are those for
Oh,
yeah.
I get
So they
point.
only need to transmit these. Yeah,
So
I think that's how they work.
So it's more like two stage. First stage they will delete the black one, so they
Yeah.
only need to focus on the remaining neuron, and
Yes.
then from the remaining neuron, they need to kind of aggregate and then decide which neuron will be further pruned.
Yes, that's my
Oh,
understanding.
okay, yeah. It makes sense. I get the point. Yeah. Okay, and then finally in this one, they tell you, well, exactly those one will be pruned if those neurons will be pruned if your for example your original model had some kind of active neurons on those locations. So this one. For example, in this one, this is yellow one. So this one will be pruned after this aggregation.
Yes.
Yeah. It makes sense. Yeah, I get the point. Yeah,
That's my opinion. Yeah.
that's great. Thanks.
Okay. So
But by the way, Dr. Guo, for the binary quantization paper you mentioned, that apply to the general fed learning or that's apply to the personalized fed learning? I think here, personalized, just like you mentioned, right? So the guys only will aggregate the neural they're interested in, or say is originally in their previous structure, right? For the rest of it, they just don't care about that, just like the right side figure show here.
Yeah. But for the binary quantization paper, I think it's basically like they don't have the so-called personalization issue. They don't consider personalization. It's a distributed optimization, distributed learning. It's not a federated learning. So they don't need to consider the personalization. And also they don't really need to consider the computation because they're talking about data center. In the cell phone, the computation is not an issue. Only the communication is an issue. So, but I can sense that this one should be their motivation should come from that part, from that paper, the binary quantization, and then they will match this one. They integrate this one with the model pruning. I think that's what they are doing, that they model this under personalization. I don't think personalization is a big issue here. It's just like personalization is basically like, everyone just use a different pruning mask.
Yeah,
that's
pruning
it.
mask.
Yeah. I didn't say how they do it. Well, personalization is not that difficult if you just want to, bring into that structure. It's just like everyone just integrate your data to the model, to your own model more than other device data. Then you will get a personalized model because everyone will learn a different model. I think that's not a big issue. It's just trying to sell the paper. They mentioned that, but I think the key thing is that they integrate.
Exactly. That's the reason why I want to ask: did they abuse the concept of personalization or not? Because according to my general understanding, personalized fed learning is like different device, you have different loss function, right? You target at. That's the general personalization. But here is the things is they just change the different prune structure of the model. Or the same
agree.
model.
Yeah. They remember they I think they still they are actually still not personalized in terms of data distribution. They are personalized just because everyone just have a different initialized pruning or initialized model or mask, and then we are still using, as Huai-an said, we're actually still using the same common aggregated mask. It's just like because our initial points are different, and even given the same common mask, everyone just get a different model in each situation as well, just because our starting point is different.
Yeah, Paula, I want to redirect the question to you. So do you think it's kind of an acceptable definition of personalization? Have you ever, come across another paper define the personalization like this?
No, Dr. Pan, I think I would kind of agree with you in terms of the personalization that this paper is using. It's not exactly like the personalization that we have seen in the other works, which totally focus on that. I don't think it's the same way in this.
Okay, yeah. Yeah, Huai-an, please go on. Yeah.
Okay, so yeah, after the aggregation, the process will continue, and after an amount, they would do the final personalized model generation. So based on this picture, you can see that each model, they have given a different personalized model, and what they did is that as we just shown here, so they have the same frozen local model. So the local model are all still the same. What it is different is that they have their own heterogeneous binary mask. And after this, they can generate their own personalized model. And that, I think that's how they they mentioned about the personalization part. And since all these process, the binary math, they're only 0 and 1s. So the computation will be more efficient, so that improves the computation part of this. So that is pretty much the overall contribution of the FedMask. So you have all these yes.
One second, sorry for interrupting. Can you go back to the previous slide?
Okay. Yeah.
I just have one question. So like, so far from all the explanation that we've seen, when they mean the heterogeneous mask, I feel they're more about talking about the system heterogeneity, maybe, like, because structurally is what they're focusing, right?
Yes.
I don't still see how they're personalizing this with respect to the data. So do they have anything specific to the data of every device when they speak about the heterogeneous mask? Or is it just the structural heterogeneity?
I think it's just the structure of this heterogeneity. So
right?
Yeah, those that determines the difference of those masks is just those, how many of those are 1 and what are those that are zeros.
Right. So when they kind of emphasize on the real value mask that they talk about, do they show how the data is influencing that value, or do they not? I couldn't go through it, so I wanted to know. When they choose the mask, do they tell how your...
do you mean like how they initialize the mask, or how they...
No, when they optimize the mask, do they also consider the data of every device? Because I see that they have like several kind of equations that they talk about in how they are optimizing this. So do they consider the data or not?
They do mention it in the data, in the optimization. As you can see, there is the data, and you have this update with the X non-ID data and Y as the ground truth label. So I think they still have an impact in the optimization given the data here. Yeah.
Do they show any kind of equation or exact connection how your X and Y is influencing your D, M?
The one they provide here is basically here the optimization. They just say Y equals this mask and times X. That's that is the information they gave here.
Okay, but this is very generic. You know that, right? It does not really include anything. Okay, that's what I wanted to know. You can go ahead. Thank you.
Okay. Yes. So after that is the overall contribution distribution. So what FedMask framework way they claim is they have communication efficiency, computation efficiency, and personalization. And you will get this personalized and computation efficient model for all your devices. Okay, so we're done with that. We would have the application and model. So they have these three. First is the image classification, and which is based on the VGG model, and the human activity recognition, which is based on a 3-layer fully connected neural network, and the next character prediction, which is based on an RNN model. So these are the 3 applications they do, and that is their implementation setup in terms of applications. As for data sets and devices, and data sets, they have these in IMIS, CFAR, HAR, Shakespeare, and a number of samples here, and a number of classes. And these are the devices they use for Jetson TX2, Jetson Nano, and Switch, and the Raspberry Pi. So these are the data set devices. And the baselines, these are the ones they are compared with. So standalone is just doing the local data training only. Fed average, which is the federal learning we know nowadays, and the top K is that they select the largest K elements of the gradients, and they do the federal learning. And the binary neural network federal average, they pretty much they do the training with only binary neural network, so it's very small. And this is the personalized federated learning average. So this is pretty much with their personalization. And this is the local global federated average, which it has local representations on the globals with reduces, which since they are doing this on local representation, so they can reduce the communication parameters. You can have less parameters that needs to be transmitted, and also because it's local, so they have personalization. So these are the baselines, and what this FedMask is trying to tackle is to compare.
I have a question about the last one.
Yes.
I think the number 4 BNN one is like what similar to Dr. Guo mentioned, like binary quantization.
Yes. Yes.
Yeah. This
Oh.
one. Yeah, for the
sorry.
yeah, sorry.
For the binary weight, it just means the weight is either 0 or 1. It's the quantization.
Yeah.
It says it is an inherited sparse model with binary weights. Yeah. They only have like binary neural. Like so you have a neural network with only 0 or 1s. That's pretty much.
They just use a different name, a similar thing. Not big deal. I just want to ask for the last personalized one, what kind of personalization, in those papers? Is it just similar to what this paper mentioned? You use a personalized structure, or it follows the general concept of personalization?
I think they follow the general concept of personalization. So it's like different from this paper. Like this paper has shown like the pretty much the structure. Yeah.
Then why do they? Oh, I don't understand. That's a different personalization. What's the purpose of comparison? Are you sure about this?
Yeah, as far as my understanding, I checked the paper. Yeah.
You checked the paper.
Yeah.
They have a different way to define the personalization, right?
Yes. The basic kind of personalization is to find the personalized model for them, but in this paper, I think they have different methods compared.
Okay.
Yes.
All right. So for the last one, what do you mean by the local representation which reduce communication parameters? So
because you have this you do it in a local place. So in a global, you have the global models, but you do the local representation locally. So what that means is that you don't need to have that much parameters to do the whole training part. And with that, you only need to communicate those parameters because they're only local. So
is it similar? Is it similar like I have a mask here, but when you do the updates, you still do the I don't know the carded local model updates. You still transmit it with a true value, but it's not like you transmit with the mask, but you transmit with the true value local model updates, but you only care about the things you're interested in. For the rest of one, you leave them to zeros. Similar to this one.
Yeah, they only care about the ones they. So that's why it's called the local. Yeah.
But for this one, yeah, I think the performance LG Federal average should be very similar to theirs, right?
I
mean learning performance. I'm not talking about the communication. I'm talking about the learning performance.
Actually, in the learning performance, as shown here, this is really similar actually. Like they are close to 80%. So the gray one is the local Fed average. So yes, they do have a somewhat similar accuracy, but in terms of communication, like FedMask explained that they have very good reduced time. Yes.
For the binary one, the performance is really bad, but the communication part is similar.
Yes, and in fact, they have.
Okay.
I will be talking about those.
Okay. Yeah.
Okay. Actually, yeah. I'll just get to this part. So this is the training performance. So as we can all see, that the FedMask is located here, and the y-axis is the communication time. So the lower, the better. And in here, FedMask has a really good communication time. And in terms of accuracy, it also performs fairly well, at least given with their results. And these are just 4 different types of data sets, and they have reached similar results here.
And Huai-an,
yes.
Is there, have you talked about the data set?
Yes, right here, here.
So how do they, so this is a data set, that's fine. But how do they simulate a long IID distribution? I mean, they need to, I assume that they need to simulate a long IID distribution setting, and then because they're talking about personalization, right? So they need to give us an idea about what's the accuracy on each device, and then take the average across different devices. So, and now if you want to evaluate the personalization, the data distribution, I mean, how do you partition the data and select the training and testing data set? That's very important to evaluate the personalization. I mean, just for personalization. Here, the info, for example, the inference accuracy here. We talk about the inference accuracy.
Yes.
How do they calculate the inference accuracy if you are talking about some personalized model? For example, this one, because you will have different models, right? Each device will have different models.
Yes, they have different. Actually, they have the same model. The models are only just based on the applications themselves. Like in the results part, they only have the like each application, they have their corresponding models.
Yeah. I mean, no. What I mean is that, for example, if I talk about image classification job, then if you are using some personalized federated learning method, then each device will learn a different VGG model. Well, for the averaging, you only have same global model. That's the VGG model. Okay. Now, if you have only the same model, it's easy for you to check the accuracy. but you have a personalized model because if you have 64 devices, then you will have 64 different models. So how do they calculate this inference accuracy in this case? Do they take an average? I don't think it is directly taking the average because different devices, they will have different data distribution.
Okay.
You get my point? So it's a little bit tricky in the if you're talking about personalization.
Yeah, they don't really give a clear explanation of how they are done with the accuracy. They just say that okay, and in compared to
Did they work on the IID data? Did they show any kind of
they
result
don't have
from that?
they only show the non-IID case.
Non-IID case. They only
Yeah,
show non-IID case.
Yes, they only have the non-IID.
No, then I share the same concern with Dr. Guo. If the ID, yeah, probably.
Yeah. I think if you go, maybe Pavlov knows that if Pavlov can pull out any kind of paper that deal with personalization, you will see that, well, if you are talking about personalized federated learning, the experimental evaluation is a little bit different compared to the kind of, for example, single model. Because now, different devices, they have different data distribution, they have different models.
Yes.
So the accuracy, I remember that when they draw the accuracy, they need to, it's not just a one number, actually, they need to go more details because now you are talking about multiple models evaluated on quite different data distribution. So the evaluation is more complicated.
Okay. So yeah. So I think that's why they only could include a non-IID case for this.
Yeah, but that's also related to Dr. Pan's concern as well. So are they really working on personalization? If it's personalization, I don't know.
Maybe they only have the concept of personalization.
Yeah, I don't think they share the same concept with the last two personalized learning model approach. So I don't know if the comparison is fair or not. We do have that concern.
Yeah, and also honestly, if you really check the evaluation result, if you have done any experiment, you will see, they compare. I think they compare 7 different methods, the baselines. But remember, if you are going to compare them, each of them needs to be tuned to be the optimal one, and that's very difficult. That's not an easy job, and honestly, if you, I'm not sure if they gave you the all the exact or all the detailed hyperparameter tuning results. Then you can repeat it. Otherwise, it's very hard for you to repeat because each method, there are too many hyperparameters to tune. And then you need to compare the best performance.
Did they provide the code?
In this paper?
I mean, in general. The SenSys paper, I'm not sure they published the code online. NAIPS, they published the code, right?
Yeah.
Maybe I might need to check on that.
Yeah, okay.
Yeah. Or what you can see in the paper, whether they talk about, for example, for each method, how do they tune that approach, that algorithm? They need to, for example, learning rate, the update period, are they using the grid search, and what kind of grid they are using, and which, if you check the rigorous machine learning or AI paper, that's very important. If you are going to submit a paper there, they will need you to have those kind of very detailed hyperparameter tuning method and baseline, the optimal value there, so that they can repeat the results. But for SenSys or MobiSys, maybe is a different community. They don't have those concern, or I don't know. Maybe
I think their selling point is still like communication efficient. Probably, I don't know, but fundamentally, I don't think those comparisons are fair. That's the key issue. I mean, definitely that's related to the later part, hyperparameter selection, tuning, everything Dr. Guo mentioned. But at the beginning, I don't even think it's a fair comparison, because they have different definitions of the personalization. How can you put them together, right? So
yeah, I think that the major issue is that, you know, they don't have a very strong theoretical reasoning about
no.
why.
It's a SenSys paper. They don't provide us.
Okay.
Yeah, that's the style of the Mobiuses and SenSys.
Oh yeah.
You don't need a reason for that.
Yeah. I get the point. Yeah. Oh yeah, it may be different community, different style. So
yeah, if NIPS, I definitely agree with you. You need to show everything very explicitly, but for SenSys, probably more people care about the system you have developed, and you can verify your ideas somehow.
But do you have a system?
Yeah, they have a system. They have
system is pretty...
Raspberry Pi 4. They evaluate the communication part. Yeah.
But do they? But for example, if you're talking about, let's say if you're talking about energy, then you have to measure the energy, you know, using some equipment, right? It's not like this is more still like a simulation. To me, it's more like a still simulation. Because, for example, they're talking about the communication cost, but then the communication cost is actually by calculation. They say, well, the model is this, right? I just time the model size. It's more like a simulation. I don't think this is a real experimentation, right? Experimentation, you have overhead, a lot of overhead, right?
Could you go to the
you measure the real size
figure? Yeah, could you go to the experiment figure for the communication cost part? Do they? Yeah. Do they?
Okay.
No, the figure part. I want to check if. Did you get Dr. Guo's point?
Yes.
Not the running time. You go to the communication cost. Okay. How do they measure the communication cost?
Here.
So what do you mean? Oh, normalize the communication time. Well, they use the communication time. They use a delay or something.
Yeah.
They normalize that. I got your point, but you know, it's still they put that into the system and measure something. Yeah.
To my perspective, I feel that it is still simulation, not experimentation. It's still simulation, like what we have done before. You know, you can estimate how many rounds you want to run, and then you know you kind of assume that the model size is the size of the model. Then you just time the rounds. Then you will be able to get the communication cost. I think that's the simulation. But for example, if they implement this system in using the Raspberry Pi or Jetson, they should have some tools to, for example, measure the time, measure the cost, right? In order to transmit a 1 megabyte model, it takes more than 1 megabyte. Yeah. Because you have an overhead, right?
Yeah, Huai-an, did they mention the measure the tools here? I think if they talk about the normalized communication time, they should talk about, based on what software tools, you measure the delay or time, whatever you call. Did they mention this? Like Dr. Guo Machine is more like simulation, or it's more like experiments?
They
Oh,
they didn't really mention they in the communication cost, they just say they measure the time and of both uploading and downloading, and then they normalize it.
I think probably Raspberry Pi, you can measure that, the turnaround time. They have some embedded software to do that.
Yeah. I think that's right. That's right. Yeah, I think they don't really measure the communication cost here. Just the time.
Yeah, just time.
Yeah,
Yeah,
time
they
they
only
measure.
have-
Yeah.
yes.
It's hard to say. You can still call it experiments.
Yeah.
It's not like the general simulation. You only care about the number of rounds, right? So you still
Oh
measure time.
yeah. That's right. That's
Yeah.
right. Yeah, I agree. Yeah. Oh yeah. They also mentioned that they measured. I think in the paper they use some kind of power monitor to measure the power consumption.
Do they provide a power figure? I don't think they provide a power.
They have they use the
They do have one about the energy consumption.
Yeah,
and
they-
runtime.
I think their results they mentioned about some I think the energy maybe is more like the I don't know what's the result running performance.
Energy, I think, is a byproduct. It's not big deal. I think,
Yeah.
time is more important. Yeah. Why don't please continue?
Okay, so this is the this training performance, and as for a comparison with a normalized time.
So what is the
this
baseline
comparison
here?
with baseline and FedMask. And
What is the baseline?
Okay, say again.
Well, what is the baseline algorithm?
Okay, so the so the baseline is basically those they are trying to compare with. It's just a overall explanation of those compare with the FedMask.
Baseline algorithm, you mean you put all those guys together?
Yes, they pretty much that's how I say. This is comparison between the FedMask and the baselines in the communication cost.
Baseline is the Federated average.
Oh, it's federal average. Oh, okay. Yeah, move on, please. Yes.
Okay, so this is the runtime performance. And we'll see that all those model sizes, because these will affect the time. So FedMask, they have this overall model size. The baseline, it has a larger model size. And the BNN, because they are all binary weights, they have very small binary size. So in terms of the performance here, FedMask baselines. So you can see the inference time FedMask had a better have a better performance than the baselines, and also in energy consumption, which are very similar results. And so the one that FedMask loses to is the BNN Fed average. But because the BNN Fed average, they are all binary, so the accuracy is very low. It's like as we just saw in previous slides. So overall, FedMask has a better performance, and so as a conclusion, the FedMask, they learn and communicate the heterogeneous mask instead of local updates, and they help devices learn personalized models, as we just see in the model generalization. And FedMask improves computation and communication. And that will be all. Thank you.
And thank you for the presentation. Any questions from other guys? I'm gonna stop recording here, okay?